So, now we are going to discuss the significance or the importance of different process parameters. Roller setting is one of the very important process parameters in draw frame. So, the setting depends upon fiber length, that is either 2.5% span length or 5% Aphyss length for cotton or staple length for man-made fibers. It also depends upon the linear density or the bulk of material between the rollers, and it also depends upon the level of entanglement and parallelization of fibers in the sliver. So, these three are very important factors that governs the setting. Here is a guideline for draft as well as roller setting on draw frame. So, draft, if you look at the table for breaker and finisher draw frame, the setting guidelines and the break drafts are shown. Breaker draw frame is the first passage that we give to the card sliver, that is known as breaker draw frame or breaker drawing process. Then the drawn slivers are again passed once more on second draw frame again, and this is known as the second passage will be known as finisher drawing passage. And if we look at this setting part now, you can see that the back zone setting for carded cotton as an example, we have chosen 2.5% span length plus 10 mm, the break draft could be 1.7, and the front zone, the draft could be the rest of the draft, because most of the draw frames will have basically 2 drafting zones, and the setting in the front zone, it is 2.5% span length plus 6 mm. Therefore, if we look at and compare the settings between the front and back zone, what we see is that in the back zone span length plus 10 millimeter, in the front zone it is span length plus 6 mm, and same is true for the finisher passage also. The setting in the back zone is again 2.5% span length plus 12 mm, and in the front zone it is 2.5% span length plus 8 mm. The setting can be done on the basis of Aphyss 5% length as well. So, generally what we have seen from this table is this, that the setting in back zone is little wider than the setting in the front zone. Now, why it is wider? What are the reasons? So, we are discussing right now about the breaker draw frame passage, all right. So, what happens that we feed card sliver and there are a lot of entanglements of fibers in the card sliver. So, because of these entanglements which are present and fiber also highly crimped and in a hooked state, the sliver can extend more. So, a card sliver has the ability to extend more in comparison to the drawn sliver or combed sliver made from the same fiber. So, because it can extend more before the sliding action actually starts, hence we need a little wider setting in the back zone, so that we make sure that the sliding action commences, and before that the sliver has to extend. So, sufficient space has to be there to accommodate the extended sliver. Other thing is that there is a high drafting force due to fiber entanglement and bulk being more in the back zone. In the back zone always the mass of material is more, and because of the presence of entanglement there will be very high drafting force. The high drafting force may lead to plucking of fibers from the back roller nip. So, we will not allow the drafting force to increase too much, and hence what we have to do? We have to reduce the force, and we can achieve it by widening the setting. That is why we have to keep the setting little wider also in the back zone. If we compare the setting between breaker and finisher draw frame, you have to understand what is the difference in the sliver which are fed to the breaker draw frame and which are fed to the finisher draw frame. What we have seen is this, that their setting are little wider in the breaker than in the finisher. In the finisher, there is also a chance for the setting to be kept at a higher level, because of the reason which is stated here, that once the fibers or the slivers have undergone one draw frame passages, there is an increase in the extent of fiber. There is a lot of straightening out action which has happened, and because of this straightening out actions and removal of hooks, removal of crimps, the on an average the fibers have extended now. Now, when the fibers are little longer because of being straightened out, we have to keep a little increase setting in the back zone and also in the front zone. Therefore, in the finisher draw frame, we keep a little higher setting in comparison to the breaker, because fiber extent has changed, fibers have straightened out, and hence we require little more setting, that is wider distance between the roller nips. Now, what is the influence of roller setting? If we look at the diagram which is on the right hand side top part, what we see here, that as we increase setting, the irregularity of the drafted product is going to decline first and then is going to increase. So, it passes through a minima, and we have already discussed this point in some other previous lectures. So, it is almost it is going to repeat it again. So, there is always an optimum setting between the rollers at which the irregularity in the delivered sliver becomes minimum. If the setting is increased beyond this optimum, the irregularity increases, as there will be inadequate control on the movement of short fiber, because if we increase the setting too much, most of the fibers will behave like short fibers, and therefore, they will move in a erratic manner within the drafting zone, and as a result there will be increase in irregularity. When the setting is low, the irregularity may also increase, as many fibers will be simultaneously gripped or nipped by both the nips of the drafting rollers, and they will be pulled out in the form of a bunch from the back roller nip, and hence there is an increase in irregularity. So, that is why we get a minimum. Too wide setting is bad, too narrow setting is also bad. Therefore, keeping in mind the length of the fibers and the proportion of short fibers which are there, we have to find out what is the right setting that we should keep, so that we can minimize the generation of irregularity. It is not that we will be able to avoid the generation of irregularity. Any drafting will always lead to some increase in irregularity, but we have to try to minimize the generation by optimally adjusting the setting between the rollers. Influence of sliver hank or sliver bulk. Now, this diagram which is shown here, we are showing here how with the increase in setting, how the irregularity is changing for a single sliver, for a double sliver, and for 6 slivers combined together. So, there are 3 different color lines indicating the number of slivers being fed to the machine. With the optimum setting, if we feed more slivers to the drafting unit, drafting wave will be visible in the delivered sliver. Why? With increase in sliver bulk, because as we feed more sliver, bulk of material is going to increase, the drafting force is going to increase, which may cause fibers to be plucked from the back roller nib, causing a rise in irregularity. So, the optimum setting that we get for single sliver, let us say, if I keep the setting at that level and feed 2 slivers, then we will find that we are not getting an optimum there. We have to move towards the right hand side, and we will get a new setting where we will find the optima for double slivers being fed together. Similarly, at that level of setting which we have obtained for 2 slivers, if I increase the number of slivers, that is from 2 to if we go to 6, then we will find that one is there is increase in the irregularity, and that the minima, the optimum setting is actually shifting towards the right hand side. It is all because there is an increase in bulk, there is increase in drafting force. So, now the situation is different when I feed more and more sliver, and again I have to find out where the new optima is. So, depending upon the number of sliver that we feed, bulk being different, we have to find out where is the new optima. So, as we change the number of sliver that we feed, we have to again find out where the new optimum lies as we move from 5 sliver to 6, 6 to 7, 7 to 8. Other than setting, the next process parameter is the delivery rate. At what speed we should produce the sliver. The delivery rate has to be judiciously decided based on type of fiber, that is whether the fiber is man made or cotton, and if it is cotton, whether it is carded cotton or combed cotton, and it also depends upon the condition of the machine, how old the machine is, what is the recommended speed suggested by the machine manufacturers. Whenever we buy a machine, the machine manufacturer suggests certain speed for different fibers. So, they already know that at what speed the machine should run from the engineering point of view. Going beyond the recommended speed, whatever has been suggested by the machine manufacturers, may lead to 2 things. One is roller vibration and noise. The vibration will introduce irregularity into the drafted sliver. That is why the machine manufacturers suggest certain speed, and one should not try to go beyond that speed in order to enhance the productivity, because the engineering design of the machine in terms of bearing, in terms of the load that is acting on different parts, the dynamic forces which acts on the machine parts, all these are designed for a certain range of speeds only. If I go beyond that, then there is a chance of vibration, there is a chance of noise, and hence any vibration will lead to generation of irregularity. But typically the speeds which are used are also shown on the right hand side. For man made fiber, it can vary between 300 to 500 meters per minute, combed cotton 300 to 600 meters per minute, carded cotton 400 to 800 meters per minute, and viscose rayon 400 to 800 meters per minute. So, what we see that for carded cotton and viscose rayon, the range of speed is little more than combed cotton or more in comparison to man-made fibers. So, what is the reason for this? While processing man-made fibers other than viscose rayon is the only exceptions, where we have seen that the speeds of processing is same or similar to what we keep for carded cotton. But for other fiber like polyesters, let us say, which is very popular fibers and processed, the speed is less. We will discuss why the speed is less. The other factors which can affect the speeds are fineness of the fiber. The fibers are very fine, even for cotton fiber, if the fibers are fine, then we have to reduce the speed, because the incidence of frequent lapping, that we have to remember that the rollers get lapped. The drafted wave has a tendency to follow the curvature of the roller, and at times they follow it and gets wrapped around it, and that leads to basically breakage of this fiber, or it may lead to thin plates getting generated in this fiber. So, this lapping incidence has to be reduced, and this is more with fine fibers, because fine fibers are, they have less bending rigidity, they are flexible in comparison to coarse fibers. So, we find incidence of lapping more on fine fibers. So, for the same type of fiber, if it is cotton or if it is polyester, if we go from coarse to finer side, then also we have to reduce the speed. Fibers with considerable crimp leads to drafting problem, because the crimpy fiber behave like springs within the drafting zone. So, they extend, and when they are suddenly released, they retract. So, this extension and retraction is a source of irregular degeneration in the drafting zone. So, fibers which are too crimpy also lead to different types of drafting problem, and therefore, we have to reduce the speed when we have too much of crimp in fibers. Fibers with poor spin finish, with synthetic fibers, the spin finish is not correct, then there is a possibility of static electricity generation. Static electricity generation is a big problem with fibers like polyester, acrylic, nylon, and hence whenever we try to process these fibers, we have to reduce the speed, the production speed, in comparison to what we can keep for cotton or for viscose rayon, because viscose rayon and cotton do not have this problem of generation of static electricity, because they are hygroscopic fiber, they can absorb moisture, and hence the possibilities of static electricity generation is not there with viscose rayon and cotton. Too long a fibers means very high dynamic drafting force. Drafting force will increase, because the fibers being long, there is a lot of contact between this fiber and its neighbors. The surface area is more, and therefore, drafting force is going to increase phenomenally with long fibers, and that could be a chance of uncontrolled drafting and also possibilities of roller lapping. So, when we process long fibers, we have to reduce the speed of production. So, with synthetic fibers, chances of static generation is there, and that is why we reduce speed. And the other issue for between, if we compare between card sliver and the comb sliver, with comb sliver we reduce speed, because comb sliver, what is the difference between comb sliver and carded sliver? The difference is, in the comb sliver the short fibers are not there, and because of the combing actions, all the fibers are very straight and parallel. So, fibers are highly parallel, they have been separated by the combing needles, which you will learn later, and therefore, comb fibers are very weak as well, because of removal of crimp from fiber and parallelization between the fibers. There is no interlocking between the fibers, too much parallelization is there. And these comb fiber or comb fiber, yes, the fibers in comb fibers are also prone to lapping around the rollers. So, to avoid this lapping tendency, we have to also reduce speed while processing coned material. Okay. Now, from the speed we move to the next parameter, which is roller pressure. Top rollers, as we all know, are pressed against the bottom roller, so that the fibers are held by the rollers firmly and move it at its speed. So, all the rollers are pressed against each other. There is a pressure. The pressure is to the order of 60 to 80 kg force, very high level of pressures we generally apply, and we make sure that the top one, which is friction driven, gets its drive from the bottom one, though in between there is a layer of fibers which is lying. The back roller pressure is little more than the front roller pressure. The reason is simple: the bulk of material is more between the back rollers, because as the material comes to the front roller side, there is a draft which is acting, the fiber is thinning. So, as the material is thinned down, the mass of material is less, and hence we can have less force on the rollers. So, on the back roller more force or more pressure, on the front rollers less force, because fiber bulk is less there. The other thing is, man-made fibers are very smooth and slippery, and in the man-made fiber there is no short fibers, as we have found them in the case of cotton. So, being very long, most of the fibers are long, and the surface area of contact is also more. Hence, what happens? Higher force is required to grip them effectively between the rollers and transmit motion to them. This is the reason. See, cotton has convolutions, the surface of viscose rayon have serrations. So, the surface of cotton or viscose rayon is little rough in comparison to the cylindrical fibers, like let us say polyester or nylon. Acrylic, even though acrylic cross section is not really circular, but the surface of the fiber is very slippery. So, these fibers are slippery in nature, the surface of these fibers, and hence if you want to grip them, we need more force on them, and that is why the pressure on the roller will be more if we are processing synthetic fibers other than viscose rayon. And not only that, viscose rayon also we increase pressure to the extent of 20 to 30%, because viscose rayon, even though surface is serrated, still the surface is smooth in comparison to cotton. So, with viscose rayon also the pressure is increased by 20 to 30%, whereas for polyester it can increase by 30 to 40%. So, remember this, that whenever we process man-made fibers, pressure needs to be raised, because the surface is slippery. Within synthetic fibers there could be different types of cross sections, but even then the surface of these fibers are much slippery in nature in comparison to what we see in the case of cotton. We can find out how much pressure is acting, if n slivers each of with W are pressed together by a force F on them, then the normal force per unit width of the sliver is going to be F by n W. Here there is an assumption. Assumption is that if we have n number of slivers in between two rollers, then the contact is only established between the fiber and the roller. The rollers are quite long enough, so that they can accommodate 6 or 8 slivers side by side. So, we are assuming that beyond the width of the n number of slivers that we are fitting, the rollers are not in contact with each other. So, entire pressure that we keep on the top roller is getting transmitted through the fibers to the bottom roller only, and therefore, we can say the force on them is going to be F by n W. Inadequate roller pressure may lead to roller slippage. On the contrary, too excessive pressure may bend the bottom rollers and would require more energy to run them. So, between these two contrary requirements, we have to find out what is the optimum pressure that we need. So, a typical pressure, suppose say of 70 kg force with the typical sliver in a compressed state is going to be around 2.5 centimeter, almost an inch, and if I feed 8 slivers, then the pressure per unit width is shown here is around 34.3 Newton per centimeter or 3.5 kg per centimeter. That much pressure we require to grip the material effectively between the rollers. Another parameter is tension draft. This tension draft generally does not get much attention or much importance, but it is sometimes become very significant, its influence. Tension draft is employed to ensure that the sliver or the fibrous web remain in a taut state while being processed. So, there are regions where tension draft is applied. What are those regions? Let us first try to look at. The locations are between the front drafting roller and coiler calendar roller. Front drafting roller, that is the delivery rollers of the machine, and the calendar rollers with it there in the coiler. Between these two, there is a certain distance the material has to travel, and we do not allow the material to accumulate. So, there has to be little tension, and the small tension is known as tension draft. So, that draft is generally little more than 1, but we will see that it could be less than 1 also. Why it is, we will discuss this. The other location is between sliver guiding roller and back roller of the drafting system, that is the creel draft. That in the creel, as you lift the sliver from the can, and the sliver as directed or guided towards the drafting unit, there is a little tension that we keep on the sliver, and there is a tension draft there, is also known as creel draft. So, the magnitude of draft is always close to 1, it is generally little more than 1. So, the table shows here the kind of creel draft we keep 1.01, 1.02, that is the typical. That means, the speed of the guiding roller is little less than the surface speed of the back roller of the drawing system. If we look at the tension draft in the breaker and finisher stage, one important difference is for the breaker machine, the tension draft, the wave tension draft is little less than 1. The draft being less than 1, what does it mean? It basically means that there is a feeding is more than the delivery. That is, I am feeding more length and taking out less. So, there is a chance of accumulation. Still we keep a draft which is less than 1, but the finisher we keep a draft more than 1 as usual, but not too much. You have to remember, as a draft of 1.05, 1.06 we should not keep to keep the material under taut state, because that will lead to irregularity into the drafted product, because such a long distance they are travelling, there is no guidance to them. If the stretch is too much, then there is going to be sliding action between fibers, and as any sliding means drafting actions, and drafting action basically means there is a chance of development of irregularity, and therefore, we have to ensure that the tension draft should not be high enough, which can lead to sliding between the fibers. Now, why tension draft is less than 1, that we need to discuss. The tension draft depends upon the elasticity of this fiber or the drafted wave, which in turn is affected by the nature of fiber, the crimp in the fiber, the degree of fiber entanglement within this fiber. These are the important factors which decides the elasticity of the fiber. The drafted wave that moves out from the delivery roller, when released from the front roller nib, it retracts. While the fibers are being processed, they are under tension from back zone to front zone. As soon as they are released from the front roller nib, before they reach the coiler calendar roller, there is a sudden scope for relaxation, and the fiber drafted wave can retract. The retractions, if there is retract, tension will develop in the wave, and which will lead to uncontrolled sliding between fibers, and that may result in irregularity. Therefore, to counter this, the wave tension draft we have to keep less than 1. So, if the possibilities of retraction is there, because the fibers are retractable in nature, then we must keep a draft which is less than 1. So, that even if they try to contract, we are taking out less, feeding more. So, therefore, the possibilities of sliding action will not be there. But by the time the fiber goes to the finisher drawing stage, there is not much crimp and entanglement left in the finisher fiber, and hence tension draft more than 1 is to be maintained. This is the tension draft, the wave tension draft which we maintain less than 1 is in the breaker stage while processing cotton, because by the time the material goes to the next draw frame stage, that is finisher drawing stage, the crimps are no more there in the fiber, they have all lost most of it, and because there is another passage of drawing, the fibers are passing through, and entanglement also less, the retraction possibilities it goes down, and therefore, we keep a tension draft which is more than 1 when you go to the finisher drawing stage. Influence of drawing on fiber configurations. Now, what is the purpose of drawing? If you go back to the original objectives of drawing, you will find that one of the purposes of drawing is to paralyze the fibers, to unhook the fibers, to improve their orientations and all. So, this particular table gives you an idea, is trying to quantify what happens to the hooked fiber that we see in the card fiber. So, if we look at this table, then what we find in the last row, percentage of reduction in hook. Okay. So, what we see here, that if I go by the column number 1, trailing hooks reduction is 68.4%, leading hook reduction is 42.1%. So, these values if you see, there is a tremendous improvement in the hooked fibers, and we have categorized the fiber in terms of trailing hook, leading hook, both end hook, U hook in trailing direction and U hook in leading directions. All types of hooks are here, and there are straight fibers S and O means others. Different categories of fibers are there, and what we see here is that there is a, in each category there is a improvement. Hooks are going down and straight fibers are also increasing. Overall there is an improvement. That is what happens, that is, as we process the material, that is from on the breaker drop frame and finisher's drop frame stage, there is a tremendous improvement in the overall configuration of the fiber. That is, fibers are becoming more and more straight, more and more parallel, and the hooked part of the fiber, hooks are basically vanishing. So, in the end there will be very little hooks which will be left. There is always a next question comes to our mind, that why do you need 2 drop frame passages or 3 passages. So, we will see that one of the reason why do you need 2 drop frame passages is to ensure that most of the hooks which we see in card slivers are removed to the maximum extent. Now, if we study this particular diagram carefully and we see that the 2 types of hooked fiber that we find in the card web or in the card sliver, they are represented by 2 different colors. So, trailing hooks are represented by the orange color and the leading hooks by the blue color. So, in the card can you see from the wave as it enters, and you have seen already that in a card wave or in a card sliver, with reference to the direction of delivery, trailing hooks are more in number than leading hooks. So, let us concentrate on these 2 types of hook, trailing hook and leading hook. So, in the card sliver, trailing hooks are more, and this trailing hook, leading hook definition is with respect to the direction of delivery from the carding machine. Now, when this sliver is packed in a can and then withdrawn, there is a reversal, that what goes in first that moves out last from the can. So, the part of the sliver that goes first that remains at the bottom, and the part that goes last is withdrawal first. So, there is a reversal. Because of the reversal, there is a direction change of the hooked ends also. So, when we remove sliver from the card can, there is a change in direction. So, what we see here in the first drop frame passage, the trailing hooks are being fed in the leading directions and leading hooks are being fed in the trailing directions. If you look at the diagram, the trailing hooks, this is in orange color, it is being fed in the leading direction, because there is a reversal, because the sliver has been packed into a the can, and from the can we are removing the sliver. So, there is a reversal. Now, in a drop frame, the drafting operation helps in removing trailing hooks more than leading hooks, because of the sliding action between the 2 group of fibers within drafting zone. The any fiber with the hook at the trailing end will be straightened out easily, whereas, if a fiber same fiber is fed with a leading end hook, it is not going to be removed preferentially. So, in any drafting zone, trailing hook removal will be more in number in comparison to leading hooks, and therefore, when I pass the material to the first drop frame passage, most of the leading hooks which are there in the card sliver, they are being fed as trailing hooks now, and therefore, most of them will get removed. However, the trailing hooks in the cart sliver, which are more in number, they are being fed in leading direction. So, their removal will be less in the fast passage, and then the material moves in to the draw frame can after the fast passage, and then again we lift it and feed to the second machine, that is the finisher draw frame. So, there if we see now direction of presentation of the hooked fiber, the orange fibers are being presented in the trailing directions, and the leading hooked fibers is presented as blue fibers in the leading directions. Now, again a drafting is going on the breaker draw frame, and now what will happen, that most of the trailing hooks with reference to carding machine or card sliver are now being presented in the trailing direction in the drafting zone of the breaker draw frame. So, they will all get removed preferentially. So, second draw frame passage will be more effective in removing the trailing hooks than the leading hooks. Trailing hooks means these are trailing hooks with respect to the carding machine delivery directions, and hence what we need is at least two draw frame passages to take care of removal of trailing and leading hooks. So, whatever I have told, the same thing is being stated here, that in the first drawing passage all trailing hooks in cart sliver with respect to cart delivery are presented in trailing directions, and they do not get removed preferentially in comparison to leading hook presented in the trailing directions. Exactly this is what was stated, and the second drawing passage majority trailing hooks with respect to cart are now presented in trailing directions and are preferentially removed. Therefore, two passages are bare necessary to remove both type of hook fibers, and hence from the point of view of removal of hooked fibers, two passages are required, and the practice in the industry is also for going for two passages. Why the trailing hooks are more removed or preferentially removed? Now, if we imagine that the fiber with a trailing, which is trailing and hooked, is moving to the drafting zone, the hooked end is short. So, the leading end as soon as it is gripped by the front pair of rollers, this end is being pulled at a faster speed. The hooked end is now brushing against the slow moving fibers, and now there is a friction between the hooked end and the slow moving fibers, and therefore, the hooked end will be easily unhooked. If I now focus on the orange fiber with the hooked end at the leading part of the fiber, now when this fiber moves to the machine, the hooked end itself will get caught. So, both the limbs of the hook will be caught by the front roller nip, and now the fiber suddenly gets accelerated, but there is nothing left in the trailing part of the fiber, trailing end of the fiber. So, the hooked end remains hooked end, and their chances of removal is very low. So, leading hook removal is actually less in any draw frame passage. If the fiber end, trailing end of the fiber is having hook, that will get unhooked very easily. But one can still feel that does not mean the leading hooks will never get removed, still they get removed while they are passing through the drafting zone, because before they reach the front roller nip, the faster moving fibers are brushing against the hooked part. This fiber, let us say a fiber with a leading end hooked is gradually approaching the drafting zone and being delivered slowly into the drafting zone, but still moving at the speed of back roller. So, when the hooked part has gone middle of the drafting zone, now what is happening? This hooked part is in contact with many other fibers moving at a faster speed. Those fibers are going to now unhook this end. Therefore, some leading hooks also will get removed whenever we go for a drawing passage. So, both types of hook has a chance to be removed, but fibers with trailing end hook has a better chance of removal than the other one. In the drawing, what happens therefore, there is a removal of hooked end, there is straightening of fibers, there is improvement in homogeneity, because there is a doubling actions, and there is improvement in mass uniformity, all are achieved. The number of passages, however, are restricted to 2 usually. Why? More drawing passages make this fiber very weak progressively due to over parallelization of fibers without any further significant improvement in uniformity. So, we do not go for the third passage in general, because we do not gain much by giving one more passage. On the contrary, this fiber becomes very weak, because fibers becomes too parallel with each other. Few hooked fibers which are still left after second drawing passage get removed by the drafting processes on speed frame and ring spinning. It is not that we will be able to remove all hooked ends by giving 2 draw frame passages to the material. However, there are some more passages which are left, like combing passage is there. If not combing, speed frame is there, ring frame is there. So, there is still drafting left on speed frame and on ring spinning machine, and on these 2 machines again there is a chance or there is a scope for the removal of hooked fiber. Over parallelization on the contrary leads to frequent sliver breaks if I go for 3 passages. When the slivers are lifted from the can and fed to the speed frame. This also you have to remember, there is no point in going for 3 draw frame passages, because slivers becomes too weak and frequent breaks will be expected. When spinning is performed directly from sliver using high speed apron drafting system, let us say in vortex spinning, more than 2 passages become necessary to make the fibers thoroughly homogenized, straightened and parallel. In some specific instances where we are spinning a yarn directly from sliver, as an example vortex spinning, the drafting system is an apron drafting system there, and we feed sliver there. Now, in this case the draft is there is very high and the speed of drafting is also very high. So, in a situation like this, the input material, that is the sliver, has to be very uniform, homogenized, and the fiber has to be very parallel, because the draft in the machine is very high. So, in this kind of situation we have to go for 3 draw frame passages, but knowing that there is a chance of over parallelization and sliver may be weak. So, to compensate that, what we do, the sliver strength is maintained by compacting it, by passing it through a very narrow trumpet. So, you have to pass the material or the sliver through a narrow trumpet, there we try to compact it and we want to enhance the strength of the sliver. That is what we generally do. This particular table is giving you an idea about the influence of draw frame passage on certain property, that is uniformity, tenacity and strength of the sliver. So, cut sliver, first passage drawn sliver and second passage drawn slivers are shown here. Here is a mixing of J34 cotton and S6 cotton in the ratio of 50-50. So, what we see in here is that as we go from cut to first draw frame passage, uniformity improves, second passage also uniformity improves. Tenacity part, if we see cut sliver is stronger, or strength if we compare, cut sliver is stronger in comparison to first draw frame passage sliver, and that is little stronger than the second passage drawn sliver. So, this is the actual data which also supports the fact that with parallelization the sliver is becoming weak, strength goes down, uniformity improves. Now, we discuss another important concept called blending delay. On the draw frame, there is a scope of blending or mixing 6 to 8 slivers. So, we can quantify the mixing capability of the machine by a term known as blending delay. Blending delay time is defined as the production time difference between the first and the last sliver can being doubled together on a draw frame. That is what is the definition of blending delay is. Here, if we look at the diagram, see there are can 1, can 2 goes up to can n, and all these cans are then brought. So, these cans are being produced by one carding machine, let us say, and they are being fed to the draw frame. So, we are placing the cans as shown here 1 up to n. Generally, n could be 6 or 7 or 8, and they are being placed here one after the other, and then they are all drawn and we produce one sliver. So, material from n cans have an opportunity to get mixed together. So, the time difference in the production of the first can to the last can is an gives us an idea about the mixing of the material. Now, to find out the blending delay time, we have the following set of equations we can derive easily, very simple. Let there be n number of sliver cans which are getting doubled. M is the sliver weight in each can, there is the can capacity. B is the delivery speed of the carding machine, they are all coming from the same carding machine. At time t equal to 0, we start filling the sliver cans. All right. Time required to produce a full sliver can is m by v, where m is the weight that is there and v is the delivery speed in terms of not meters per minute, it should be actually kg per minute. Therefore, time required to feed one can is m by v minute. The first full can is produced at time t, which is t 1 is m by v minute. Enough sliver can be produced at time t equal to n into m by v minute. Therefore, blending delay time will be T n minus T 1, and that is equal to n into m by v minus m by v, and that becomes gives you, if I m by v takes common, it becomes m by v into n minus 1. So, that is the time difference of filling or producing the first can and the last can, which are getting doubled together on the draw frame. Let us say the sliver from 8 cans are being doubled together on a draw frame. The can capacity is 30 kg, the card production rate is 54 kg per hour. What would be the blending delay time? So, time taken to produce first can is 54 by 16 to 30, that is 27 minutes. Time taken to produce the 8th can is going to be 27 into 8 is 216 minutes. Therefore, blending time is going to be the difference between these two, that is 189 minutes. That means, whatever the machine is producing over 189 minutes, these material now are getting a chance to get mixed again on the draw frame. So, that is end of today's discussion, and thank you.